Anyway, so before he invented Unix, which was around 1969, 1970, he started that project. Just before that, he was a math student at Berkeley, and he came up with Thompson's construction. Okay, so Thompson's construction works like this. And remember, there are 6 kinds of regular expressions, so we don't need a very complicated algorithm. Okay, a complicated regular expression we can reduce down to our 6 ways of making regular expressions, and so we're going to ignore all the other ways. We're going to ignore things like question marks and ranges and the plus sign, for example, for one or more. All these things can be they're just abbreviations for our 6 ways of making regular expressions. So we just need to make an automaton for each of our. Well, we need a little algorithm for each of our 6 ways of making regular expressions. Okay, so the first 3 are very easy. We're going to make for the empty set. So here's an automaton that recognizes it doesn't recognize any strings. It has one start state, it has one accepting state, and there's no way to get from the start state to the accepting state, so that machine recognizes no language or no strings at all. So the language it recognizes is the empty language. Okay, uh, a language that just contains the empty string is recognized by this machine. Okay, it's pretty clear to see that the only string that will recognize is the empty string. And similarly, we can create a little machine that recognizes um, only the language that consists of one string which just has the one character A in it, where A is whatever symbol you want. Okay? All right. Now, all of these have the property that there is one start state and one accepting state, and they're different. And all the machines that we'll build using Thompson construction have exactly that property. Okay, and we're going to take advantage of that. We're going to assume that as we go forward. So check as we go, make sure that property is always true. Okay, now if we have a regular expression that talks about the concatenation of x and y, so in other words, this is the language we recognize. The language described by this regular expression consists of strings, the first part of which are described by regular expression x, and the second part of which are described by regular expression y. Okay? Well, what we can do is we can construct, using Thompson's construction, we'll construct a machine corresponding to x and a machine corresponding to y, and then we will rename and put them together. So this is where we use renaming. So, for example, let's take a real simple example. Okay, um, let's say we have 0 semicolon 1. That's our regular expression. Okay. First, I'm going to make a machine that recognizes just the language 0. Okay. So that's going to have a state 0. That's a start state. Has one transition, and final state is a label with 1. Okay? And then I can do the same thing for that language there. And what I want is I need a way to put them together. But the thing is that their states overlap. The state sets overlap, and I don't want that. So first thing I'm going to do is I'm going to rename so that my states don't overlap. All right. So let's take this one here, and I'm going to rename my states, and I'm going to be boring, and I'm going to call that state 2, and I'm going to call that state 3. Okay. Now I'm going to put these two together, and I'm going to put them together using this idea here. So I'm going to take this final state of, and take the final state here. It's not going to be final anymore. And I'm going to make an epsilon transition between that formal or final state of the first machine and the start state of the second machine, which is no longer a start state. In my final machine, I just want to have one start state. And I just have one final state. So that's what I want. Okay, so now we have a machine. Now there's a simpler machine that does the same thing, okay, but this one works. All right? All right, so that's catenation taken care of. All right. What about alternation? Well, I could do alternation in a similar way. Let's just back up to our two machines here. And yeah, so let's put them together. Let's say that was an alternation instead. So alternation. Okay. Well, let's see. First off, I'm going to alter these machines a bit. I've done my renaming, right? I compile each part, and we do the renaming so that they have disjoint state sets. Neither of these is going to be a start state, and neither of these is going to be a final state. Thomson's construction does not minimize the number of states produced. Anyway, I'm going to add some new states here. So I'm going to have a brand new start state, which I will label 4. I'm going to have a brand new final state, which I will label 5. Okay, so we get this machine. And finally, for the cleaning closure, what I can do is I can compile X to get a machine, and we'll call that A of X, and then I'll add 2 new states and these 4 new epsilon transitions. Let's look at an example. What I'll do is I'll build on this example with the alternation in it, and let's suppose that that whole thing was inside of a Kleene star. Okay. So first thing I'm going to do is compile. I'm going to compile the 0 alternation 1. So I'll compile the stuff inside the parentheses, and I'll get a machine that looks like this. Okay. And now, like I said, I'm going to add 2 new states. So before I do that, the final state here will not be final anymore. All right, but let's remember that that was the final state, and the initial state here will not be initial in the new machine. Now I'm going to have a new start state, so I will call that 6. Oops. And that's going to be a start state. I'm going to have an epsilon transition to the start state of the X machine. I'm going to have a new final state, which I'll call 7. Okay. And I'll have an epsilon transition from there. Now, so far, this machine actually recognizes just the language of X. That is, it recognizes the alternation. It's just a more complicated machine to recognize exactly the same language of 0 or 1, right? But the thing is that after recognizing 0 or 1, we go back and do it again. So that motivates this link here, transition here, which again is labeled with an epsilon, right? So now we can recognize a 0 or 1, and then followed by a 0 or 1, followed by a 0 or 1, okay? But the other possibility is that there are no repetitions at all. So that one, to take care of that 0 case, we'll also have a link here with an epsilon transition, okay? And that's it. So this is a kind of a recursive compiling algorithm for our regular expression language into non-deterministic recognizers. Now, before we go on, I just want to talk a little bit about why they are called non-deterministic. Okay, so this machine, and I won't bother giving the states names just yet, but I'm going to label that with a B. I'm going to label this with a C. All right. So what language does this represent? What language is recognized by this machine? Well, you can see that we're going to have this string just using the path definition, say. You can see there's a path from here to the final state that's labeled with AB, and there's one labeled here with AC. And those are the only two paths from the initial state to the final state. So that's in fact the whole language. Okay. So that's straightforward. But if you think of the machine as an algorithm, well, it's kind of a funny algorithm because if you think about the machine as sort of a description of how to process input, well, if the first symbol I see is an A, what state should I go to? Should I go to this state or to this state, right? So it's called non-deterministic because it doesn't really force you to make a choice. And in fact, it kind of forces you not to make a choice at this point. And we kind of have to be open-minded about what the next state is after. If we start in our start state and we see an A, the next state we're in, well, it could be this one or it could be this one. Okay. So so thinking of these things as language, well, thinking of them as algorithms is a little dodgy. Well, anyway, nevertheless, I'm going to attempt to do that, and I'm going to do that using what I call the two-finger recognition algorithm. Okay.